So, volcanoes. By popular demand, we're going to make a video about volcanoes. I love volcanoes. I think they're nifty. So, how do they work? Well, I'll tell you. First, we start off with the tectonic plate map, right? We all know how this works. All these different lines create plates, and these plates move around on the map, and each one has its own direction that it's going. So the type of volcano that you have. So first off, volcanoes mostly happen along these lines. So you're very rarely going to find a volcano outside of these lines, and if you do, it's from a hotspot. If you want to learn more about that, I have another video that you can watch on those. Check it out. But for the most part, most volcanoes are going to happen somewhere along these lines. And it depends on the type of volcano, and the type of what's happening at the line depends on two things: which direction the plate is moving, and what the plate is made of, like the type of rock. So, for instance, this Pacific plate over here is moving east towards the North American plate. Do I have that right? No, I don't. Shoot. Okay, well, we'll come up with a better example in a second. Actually, I have a better example. I'll get to that in a second. First off, well, we'll start up north. So the North American plate is moving west, and the Eurasian plate is moving east, right? So that creates what we call a divergent boundary here in Iceland, which is what creates a volcano in Iceland. And there's a lot of volcanoes in Iceland, but we'll talk about this, right? So you have these two plates going opposite directions. This is a drawing I drew in 8th grade. It's beautiful, I know. And this is what we call a divergent boundary. So as you can see, the plates go either way. The magma comes up from inside the ground to fill whatever space you have left. And as it slowly floods up over a lot of time, you build up this mound. And each time that these plates as the plates keep coming apart, the lava will come up and build higher and higher and higher. And that's what we call a shield volcano. So as you can see here, you just get slowly, as your crust moves away from each other, your magma chamber will push magma up into the vent and will slowly flow over on top of each other. So that's why, like, Iceland is growing technically, because the two halves of Iceland are going further apart and more rock is being made in the middle, which is pretty cool. So where am I? Here I am. Okay, so that's one type of plate. That's a divergent boundary between two oceanic plates, which we'll also get to. Next, we'll talk about the Juan de Fuca plate and the North American plate. So the North American plate is moving west, we've decided, and the Juan de Fuca plate is moving east. And as that happens, you have, actually, we're going to get to that one in a second. But first, we'll talk about the Indian plate. Indian plate and Eurasian plate. So the Eurasian plate is moving east, but it's also kind of moving south, and the Indian plate is moving north. So that creates a convergent boundary. And at a convergent boundary, here we are, between two continental plates, as you can see. Where am I? Shit. Oh, here we go. Okay, so as you can see, that the Indian plate and the Eurasian plate, the continents are kind of hitting each other, and that doesn't necessarily make it a continental plate, but for the most part, that does. So they're both continents. They're both coming at each other. Since they're relatively, as they're colliding, they'll both kind of crush up against each other and create a mountain range, which is why you have the Himalayas right there. Yeah, which is pretty cool. So divergent boundary goes out, and you get lava flowing up, magma flowing up in the middle, lava and spreading out and creating a shield volcano, creating more land, kind of like a big dome type of shape. On a convergent continental plate boundary, you have the two plates coming at each other, hitting each other, and just kind of creating a mountain range. So that's a lot sharper. That's like what created the Rockies and a longer time ago, the Appalachians. So all mountains were, well, actually, don't quote me on that. I don't know if the Appalachians might have been something else, but I'm not quite sure. I haven't learned about that. So yeah, so you have a mountain range from two continental plates hitting each other. But what happens if you have, and the third type of boundary, which isn't as cool in my opinion, is a transform boundary. So that if the North American plate is moving west and the Pacific plate right here is moving like kind of southish and kind of east, you get like the two continents kind of grate against each other, and that creates earthquakes. So that's why along that fault, the San Andreas Fault, you have a lot of bad earthquakes. It's because the continental plates are just kind of like rubbing against each other and just grating. Nothing good is happening. It's just making stuff hurt. So moving on, what happens if we have over here the Juan de Fuca plate and the North American plate? North American plate's going west, Juan de Fuca plate's going east, but the North American plate is a continental plate, and the Juan de Fuca plate is an oceanic plate. So what's the difference? Well, the continental plate, much thicker. That's why it's above the water, right? It's also a lot less dense, so it's just kind of like, it just kind of floats there more. And the oceanic plate is a lot more compact, it's a lot lower, and it's a lot more dense. So as you have this thicker, less dense thing coming up against this thinner, more dense thing, which is lower, they hit each other, and the oceanic plate rolls underneath the continental plate. So, and that creates what we call a subduction zone. So you can see here that the oceanic plate comes in and just subducts underneath the continental plate, and that creates a volcano. But how? Well, as you get closer to the Earth's core, stuff gets hotter. Who would have thunk? So all this oceanic crust, oceanic plate and rocks and stuff turns into magma, and that bubbles up through the continental lithosphere and crust and creates volcanoes. So that's what the Cascades are, if you know what that is, and I think the Patagonias are that as well. Interesting thing with this, you get a lot of andesite. No, sorry, not Patagonias, Andes, because andesite, Andes, right? So because it's so much andesite because you have two different kinds of rocks. The continental rocks are the lighter, whiter kind of, and the oceanic crust is like the darker, more black rocks. So as you combine the two, it creates kind of a blend. So andesite is some light and some dark, just kind of mixed together. So that's why you find andesite at that kind of zone, if you call it. All right, what else do I have? I forget. Oh, that's a good one to talk about. Okay, so another difference between oceanic and continental plates and boundaries and stuff is the different silica contents. So In each rock, you have a different silica content, which is how, like, when you melt it down, how flowy and runny it is. So you can see, like here, this is very what we call felsic. So it's like very flowy, and you can just like, you can almost just like scoop up some in a cup, you know. Um, and that happens at a oceanic kind of setting. So that's more of like Iceland has a very felsic magma. So it like comes up and just kind of like bubbles down. And Hawaii is the same thing. And Hawaii's a hotspot. Like I said, go check out my video on hotspots. But more of this. This is an ash cloud. And you don't get this at like oceanic type of settings. You get this more at like continental things. So like the Cascades are a lot of this, just because there's more mafic. Mafic is the opposite of felsic. It's just kind of harder, and as it blows up, it doesn't flow, so it just like, you know. And with this type of thing, you also get a lot more gas. So like the rock will come up and it'll cool, I guess, faster and plug the hole, and then it'll just build up more and more gas and then explode, and that's kind of what creates the smoke cloud, the ash cloud. Another thing to add with this, we hear a lot of this about this in like Iceland, but it doesn't have to be like that sort of thing. Like it can be underwater. So over here at the other side of the, like between the, I think it's Pacific plate and like the whatever this plate is, the Philippine plate or maybe the Australian plate, and also, shoot, is it right here? Yes, it is right here. Okay, so this like S thing right here, and then also down here. No. Yes. Okay, so over between the Australian plate and the Pacific plate, and then between the American plates and the Eurasian and African plates. Those are both divergent boundaries too. But so like up here in Iceland, it's built up enough to be above water, but below you just have like a ridge. So the Mid-Atlantic Ridge, that's what this is. It's just a ridge going down where there's a divergent boundary, just pushing away, and the magma's bubbling up underneath. And then it's the same thing over here, and that's pushing one way or the other. I don't know which out, I guess. No, over here. And then that's what shit is over here. I don't know, somewhere. I don't remember. But either way, hopefully that answers your question. I'll do a quick recap, I guess. So this is the most common one, subduction zone. You just have oceanic crust coming under continental crust, melting, bubbling up through the continental crust, and just creating volcanoes. That's what the Ring of Fire is around the Pacific. That's why there's a lot of volcanic activity out there. Another classic, a divergent boundary. Iceland is a great example of this. That's the video that you sent Sigurd, I think. And that's where the plates come out, and the lava comes up and bubbles out and just creates a big hump of rock. And then this isn't really a volcano, but you just have two plates coming in, creating mountain range. Himalayas is a great example. More subduction, volcanoes, shield volcanoes. All right, that's all I got.